So I'm really thrilled to introduce Silvia Zuffi. Silvia has been she's in Italy, and she works a lot with different types of 3D modeling, and she's used that in some of the work I'm most familiar with. That's quite cool, where she's actually taken 3D models for lots of different species of animals and then puts individual texture on them. So she's improved our ability to recognize individual species from many fewer images, because you can now create synthetic versions of all the different angles you might see. And she's going to be talking a bit, I think, about that, but also potentially about a bunch of other cool work that she's done. And I'm also quite excited because one of the students that I've been mentoring for the last few years is now joining Silvia's lab and being co-advised by Michael Black at Max Planck, and they're going to be working on some similar fine-grained 3D stuff for elephants. So I know Peter's very excited too, Silvia. Okay, awesome. So take it away.
Okay. So let me. Okay. Is it okay? Are my slides on?
Yeah, that was great.
Yeah, okay. Okay. Well, so first of all, I would like to thank you for inviting me, Sarah and the organizers. And I wish I was there with you, but I'm very, very glad to have this opportunity of talking about my work to this audience. And so the title of my talk is Looking at Animals in 3D. I feel a bit I've been giving similar talks for the past few years, but just changing the title. So maybe you have already seen this, some of this material, but given this is a summer school, I think I should introduce my work from the beginning. So looking at animals, so consider a picture. This is a picture with an animal in it. And it's not just a random picture. I deliberately searched for the oldest picture with an animal. I hope this is accurate. I just found it online. But as a computer vision scientist, looking at animals for me, it means to create an intelligent system that can process an image like this one, or a modern version of an image like this one, and answer questions like, is there an animal? Which species is it? What is it doing? And if we take it to the approach, so we consider the flat world of the image, this answering these questions turns into addressing computer vision problems of object detection, where we want to locate the animal in the image with a bounding box, or animal recognition, where we want to assign a species label to the bounding box. And here on the left, you see the output of Mascar CNN, where you also here get a segmentation of the animal. And pose estimation in 2D is the means to identify the location of the set of animal landmarks. And here you see an example from DeepLab Cat. I know you're already familiar with this very cool tool. So in my research, my interest is instead to look at animals in 3D. So I'm mostly interested in doing 3D pose estimation. That means to estimate the 3D rotation of the animal's body parts, and shape estimation, so estimate the real 3D shape of the animal. So for example, suppose you have this image with a cheetah, and what you want to obtain is a 3D reconstruction of the animal from this monocular data, where you have an accurate pose and shape. So I take a model-based approach. And so what is a model in my case? What is a 3D model of an animal? I consider parametric mesh-based models which are a mathematical formulation that, given shape and pose parameters, they form a template to return a 3D object. So here in this very simple equation, you have two sets of variables, beta and theta. In the presentation, beta will be always shape variables. So are typically a vector of real numbers of size, I don't know, 10, 20, 30. And they describe with this low dimensional representation, the shape of the animal, the intrinsic shape of the animal. And theta are 3D pose variables. So this is a vector of dimension, the number of body parts times 3. So for each body part, these 3 values, they represent the relative 3D rotation relative with the parent in the kinematic tree. For example, you have a model template, like here on a turtle, and then you have an image, and the 3D pose estimation here means to estimate the betas and the thetas that make the model template to the form to match the image. Okay. So I want to point out that shape is not, recovering shape is not just a problem itself, but is functional to 3D pose estimation when you use monocular data. And this for me is very important. So consider this picture with this tiger. And this on the right is a plausible 3D reconstruction of the pose. But then if you look at this reconstruction from another view, you see that the pose is wrong. There is this very natural 90-degree turn in the of the body. And this is because the model is wrong. The body is too long. And so there is this wrong 3D pose for the model to match the monocular information. So this means that when we create a 3D shape model, we need them to be accurate and expressive. Otherwise, would introduce errors when estimating 3D pose. Okay, so in summary, why a model-based approach? Because I think it's a better tool for monocular reconstruction. The model can incorporate prior knowledge about the animal, for example, the body symmetry. And with respect to skeleton models, it provides a richer estimation of pose and shape, but you can reason about the occupancy and the contact surfaces of this model because you actually reconstruct a surface. And with these models, you can also do some unsupervised learning using the photometric laws. We'll see this later. So in general, the models are useful when the data is noisy, because at the end, the model is prior knowledge in the form of what is allowed for the parameters to be. And moreover, why 3D? I think so. The word is 3D. So we, for an intelligent system, so we reason in 3D, and intelligent system should reason in 3D. So we have our 3D mental representation. The intelligent system have its formal internal space, which must be 3D. And also many questions, they have an active formulation in a 3D space. Questions of interest for you. For example, animal re-identification based on skin appearance. So there is enormous work from Wildbook that is in 2D, where you match images, provided some view information, and you do this in the image space where you compute these features and try to detect correspondences. But you can approach this problem in 3D, and this means you can fit a 3D model to animals, and then given this fit this alignment of the model to the image, you can grab from the image the texture of the animal, the texture map, and create this representation of the skin appearance in this canonical space of the texture map. And so now you can compare texture maps of different animals independently from their 3D pose. And for what regards the pose or posture analysis, so if we consider marker-based methods, so without a model, if we are in 2D, the location of these markers or landmarks is ambiguous because it depends from the relative position between the camera and the animal. So typically you would do this with a fixed global rotation between the animal and the camera. You can think of doing this landmark or marker-based methods. And in that case, you would have a more robust representation because you would be robust to these relative rotations. But in my view, this is not yet sufficient because if animals, they have a different shape, they might have a different distribution of these 3D points. So depending on the task, it would be okay or should be not perfect. But if we had a 3D model of the animal, then we can recover shape and pose, which are independent variables. Then we can compare just the 3D pose of the different animals, provided that they have the same skeleton. But so shape could also be a problem by itself, right? So you can think of doing tasks like gender from shape. In this case here, maybe here would be pregnancy from shape, I don't know. But the male and female bodies are different. And you could also think of doing age from shape, where the baby zebra has head and body proportions that are different from the adult. Okay, so I hope so far in this 15 minutes, I have convinced you of the opportunities that are out there when working with 3D, with a 3D approach. And this is a short agenda for what comes next. I will introduce the small model. And we'll talk about how to create models from images, how to recover 3D shape and pose from images, and then I will talk about more recent work on horses and dogs. Okay, so if you have questions, I don't know if maybe you can interrupt me. I can answer, or we can have the discussion all at the end. So small model, small is for skin multi-animal linear model, and is a 3D model that can represent articulated animals with shape variation across different species. And specifically, we considered species in these 5 families here, which are all characterized from being quadrupeds with a tail. And we learned a small model from real 3D data. And the model was presented as CVPR in 2017. So in computer vision years is an old model. I like to point out that small is the animal equivalent of simple. Simple is a skin multi-person linear model, and is a super popular model for representing humans. You know that computer vision research is a bit obsessed with humans. So they develop a lot of very, very cool methods. And the fact that small is so similar to simple is an advantage. So many technologies that are developed for simple can be adopted by small. So simple is this statistical shape model, which is learned from 3D scans. And so Matt Loper and colleagues, they use the CSAR data set, that is a set with thousands of 3D scans of people or standing in this A pose, which is a typical pose that is taken to reduce occlusion. And the fact that they scan all these people in this reference pose is also to facilitate the registration of the scans. To create a model, you need to put all these 3D scans in correspondence. That means they all need to be represented with the same number of 3D points. So once you have the correspondences, so all the scans represented with the same set of 3D points, you can take these 3D points and compute the average to obtain the average person body, which in this equation is mu. And then you can look at the deviations from the average person to an arbitrary person, and represent this deviation with a low-dimensional linear model, which is u times b, and again beta, which are the shape variables. So this video here represents the direction of variation of the principal components of this linear shape space. So in a way, so you have these variations, and when you specify a beta variable, you take a linear combination of all these variations to represent any person. So this is not yet sufficient for humans because so we have soft bodies, and they deform also with pose. So Simple was also learned using a data set of people doing different poses to learn how these bodies deform. So then when you articulate the simple model, you can notice that there are deformations, especially at the shoulders and at the hips that depend on the 3D pose. So in 2016, we decided to do the equivalent of Simple, and so we thought of scanning real animals, but that was not possible. So we look at few alternatives, and at the end, we decided to use toys. So we created a data set of 3D scans of toys that is shown here on the right. And so if we look at what has been done for Simple, now we know that we need to have these toys in correspondence, and we need to have them all in the same reference pose to learn the shape model. And this turned to be quite of a challenging task because at the time available methods were not, they didn't really work for us. So we designed a new registration method. As I said, the task was very, very hard because we didn't have not only pose variations, but really large shape differences. So we approached this problem by first selecting an animal of reference, and for us it was a lioness. So we randomly picked a lioness mesh, it's here on the top left, and we segmented into parts indicated with different colors. And then we designed this optimization, this registration method showing here the video, where it's an iterative procedure where each part can deform independently in order to match the scan. So if we apply this method to the toys, we obtain this really kind of funny deformed lions, sorry. And but so they have more or less the desired shape of the toys, but not really the correct features. But they have the correct 3D pose. So this is for us a starting point to do a refinement, where now with this approximated lion, you are close to the surface of the scan. So you can just move the vertices to match the surface of the scan. And here on the right, the output of this procedure is visualized in purple and the scan in white. And the fact that you see this high frequency texture means that the two meshes match very well. So to recap, we started from this 3D scans, we did the registration, and with the registration, we also have the 3D pose. So we can undo the pose and obtain the toys in this reference pose that is the 3D pose of the lion. And now we can do what Simple does and do the PCA, principal component analysis, and obtain the shape model, which is a mean shape, which doesn't represent any animal in particular, plus this low-dimensional linear model, which is characterized by this matrix of deformations that you multiply by the shape variables. And if we look at this, the deformations that we have learned, the first dimension, which is beta 0, is a size, and is here on the horizontal line. And then in the vertical is the variation that corresponds to B1, beta 1, and so on. So you see that in this shape space, we can represent all the toys with very few variables. So, sorry, let me. So now consider these beta variables for all the toys in the training set, and make a projection in a 2D space and plot them. So you obtain the plot on the right, where the big circle are the average betas for each family, and the small dots are the training set samples. And you see that we have these clusters. That mean that cow and horses and hippos are very different, while lions, cats, and dogs, they're maybe less different. And if we change the shape, the beta variables, if we move from one cluster to the other one, we can actually interpolate between these families and have an idea of how this shape space looks like. So this is at the end a generative model for shapes because you can sample the beta variables and generate animals. But if you do this using a normal Gaussian with zero mean, you obtain most of the time animals that do not exist because we have this multi-species shape space. So to obtain realistic animals, you need to sample the betas in the cluster of choice. So if you want cows, you need to sample the betas near the cluster for cows, and the same for the other families. So here, I forgot to say before, these colored meshes are they correspond to the average beta in the family. So here, this red cow is the average small cow. The yellow horse is the average small horse that looks more like a zebra, and so on. Okay, then for the articulation, we simply use linear blend skinning. We don't model pose-dependent shape deformation because we didn't have the data. And in this video, we just see random samples from small, which have been animated with this synthetic walking sequence. Okay. So then we fit small to the images, and this is from the original paper. And we do this by minimizing an energy, where we minimize over the beta, this theta, so shape and pose. T is the translation, and F is the focal length of a perspective camera. So we don't, we estimate the camera with this optimization. And the energy is the sum of a data term for key point matching and silhouette matching, plus some priors for the camera, joint limits, prior on the 3D pose and on the shape variables. And so here, this simple example with the lions shows that sometimes it's sufficient to only align to the key points. But in this case, given the lion has the mane, if you really want to get the animal shape, you need to consider also the silhouette. And then here we fit the model frame by frame. And for us, this linear blend skinning without the post-dependent deformations for the quadrupeds that we have considered, so far it works fine. But of course, if you have more deformable animals, I think you would need to improve the linear blend skinning with some more complex post-dependent deformations. Okay. So what if you want to obtain a model, or you need a model for an animal that is not in the small shape space? So you cannot do elephants, you cannot do a moose because of the very different skeleton and because of the horns. You can actually do a giraffe. So I actually learned the model for adding also the giraffe to the shape space. But that's not really useful because then you don't have enough body parts to articulate the neck. So you can only have a giraffe that has always the same pose for the neck. So maybe not that useful. But so you are stuck if you want to go to take our approach of using toys. If you want to do animals that are not possible to 3D scan, but probably nobody will ever make a toy out of them. Yeah, you can still do it because you can use images. And this is a work that we presented in 2018. So the idea here is that if you have multiple images of the same animal, even if these images are taken from internet, but it's the same animal, you don't know the camera, you don't know the 3D pose, the 3D pose is different, but there is a constancy here and it's a shape. And this, you can leverage the multiple images to actually recover the shape. So this method that is called smaller, maybe not imposter. Yeah, we like to play a bit with the names. It's for smaller plus refinement. So it works like this. You first do a small alignment. You minimize the energy that I've shown before, but this time you do it jointly on the 3 images, in this case, 3 images. And now your variables are different pose variables for the different images, different cameras, different translation, but the shape variables are the same for the 3 images. And doing this, you obtain the best approximation in the small shape space for the rhino in this case, which is this hippo/cow animal. But now, what you can do now is to do 3 vertex deformations like what we have done before for the toys, but this time only using images, in particular using the silhouette. So you take the small shape, this shape, and you add these deformations, dV, and you optimize these deformations using the same key point loss, the same silhouette loss, but now you are optimizing over, let's say, 3,000 numbers, which are the vertices. So you need some regularizers that are, in our case, as rigid as possible regularization, asymmetry, regularizer, and Laplacian smoothing. So for this to work, like in general, you need to have the animal visible, the full animal, and a simple pose. But also you need to see in the images the features that you want to recover. Like in this case, you need to see the horn of the rhino. Otherwise, if you use a silhouette, I don't know, if you have 3 images like the the one at the bottom where you don't see the horn in the silhouette, there's no way this is going to work. So, so now you have obtained this golden rhino, which is well aligned to the images. So then you can grab the colors from them and reconstruct a texture map. And then you have a rhino avatar that you can animate and print. So we also did this for the Tasmanian tiger. So here we look at this video and we selected frames again where the animal is fully visible. And yeah, when we apply this method, of course, now the output is not colored. Yeah, in the paper we have other examples. So if you want to play with this, the code is online and there are 3 demos, maybe 4, for the Tasmanian tiger, for the zebra, and also a few demos for cheetahs, where here I'm only using 1 image. So it looks okay from the side. You can rotate the 3D model and sometimes a bit squashed because you're only using 1 image. And the method assumes you have a bit more. Yeah. So we only do quadrupeds, but I know that many people, maybe some of you are interested in birds, and we don't do birds. But if you like them, and I do actually, Mark Badger is your person. And they have very cool work that are similar to what we have done for quadrupeds. Okay, so so now, okay, the first part was about creating 3D models, and now let's see how we can use the models to recover pose and shape from images. So we did this work for the gravy zebra, which I'm pretty sure you know that is the one on the left with the white belly. And here we wanted to do a direct regression from RGB data. So not using key points and silhouette at test time, just training a network for direct regression from the input image. And we wanted to do a training based only on synthetic data. Because we didn't have 3D ground truth. So in this method, we also predict texture, so not just shape and pose, but also the texture. And this not only for having pretty pictures, but also because we make the hypothesis that predicting the texture actually helps in the task of pose and shape estimation. So we got the data from Wildbook. They gave us several pictures of the same individuals. And now you can guess what we did. We created avatars. And from this, these are some of the avatars we created. And from these avatars, we created a synthetic data set with 3D ground truth. So the top is the synthetic data, where we have the foreground is the zebra, and the background is a random picture. And below is real data, and you can see that the zebras look quite similar. So the network, the regression network is simple. We have input image that is encoded in a set of features. And then we have 3 independent paths, one for texture prediction, one for shape prediction, and one that predicts the translation, the camera focal length, and the 3D pose. You put together all this information and you obtain the predicted 3D zebra. Here, the shape is represented as the average horse in the small model, plus a linear layer that is trained, which is simply sort of implements a linear shape space that is not orthogonal like the PCA space. So now, given we predict the texture, we can, at training time, we can have a loss for the 3D that exploits the 3D supervision, but also a photometric loss. And we can filter the image using the input silhouette, because of course at training time we have the silhouette. So these are results from the regression network. It works quite well, but there's room for improvement. And the improvement comes at test time. So at test time, we have the image, we predict this the zebra, and now we can use again the photometric loss. Now we don't have the silhouette, but we can use an average background, taking the average color in the input image, and optimize, minimizing this photometric loss, and optimize over the network features. And doing this improves the alignment from the initial prediction to a better match with the image. So then in the paper, we show that optimizing over the network features is better than over the model variables. And we also show the advantage of predicting the texture map. Okay. I think this works only on synthetic data because our synthetic data is very similar to the real data. But of course, challenging cases, you need to use also some 2D images. I'm going a bit quickly because I think I'm running out of time. We still have 10 minutes. So I want to point out that while we use model-based methods, now this is very exciting for me. You start seeing people that try to create 3D animals using model-free methods. And these are just two recent works, one at CVPR and one that will be presented at ACCV. And that is a model for cat. So we trained small with many animals, mostly because we didn't have a animal of choice in mind, also because we didn't have a lot of training data. But if you have enough training data, you can consider actually learning a single species model. So here I want to show you, for example, a model for horses. Here we bought more horses and we did the gloss alignment. And if you do what I explained before, you obtain a small model for horse. So here you immediately see what's wrong. So we have used the lioness to align the horses. And now the rest pose for this horse has this weird feet point, like as the feet, the rest pose of a cat. So then, my student decided to actually do something more reasonable. So use a horse to align a horse, not use a lion to align a horse. And this has the advantage, of course, of that you can have a skeleton that is more, suitable for horses. So you have an extra part for the neck, you have more parts for the legs, you have less parts for the tail, because maybe that's not so interesting. And she presented this work at CV for animals. So here she also aligned the H small model to real 3D data. This we have never done this before. For these horses, we had 3D mockup markers, which could actually align to the real horses and show that the model is okay, but there is still room for improvement. And so recently, she is working on this very cool project, in my view. So when she also uses audio for pose estimation. So the idea is this one. So when you work with animals, 3D animals, most of the time you don't have a lot of data. So in this case, maybe you will have training data for brown horses, and then you have a white horse. And then what you have learned for the brown horses doesn't work for the white horse. But if you hear, suppose you hear a horse running, That is a lot of information about the motion, and it's 3D information, because if you think that anytime the horse hits the floor, that is a sort of 3D information that you can get from the audio channel. And she showed that with this, you can have a white horse, and if you also use audio, you can still recover the correct 3D pose, even if you don't, if that is not really well represented in the training set. So dogs are also not very represented in small. And we did the same, bought more toys, create a dog model. This is a shape space. And now if you sample in this space, you have mix between different breeds, which are completely fine for dogs. But what if you don't have the 3D scans of the shape variations in the species of interest? So this is a recent work from Nadine Dreckham. She presented this at CVPR this year, and it's called BARK, Learning to Regress 3D Dog Shape from Images by Exploiting Breed Information. And this, you see some of the results of this method that in terms of shape reconstructions is completely, is clearly better than previous state of the art. So we've been inspired for this work from this article on where the author they look at the genome of the domesticated dog, and they look at the relationship between the different breeds from the genetic point of view. And this cladogram includes a lot of popular breeds, more than 100. And in colors, you see the different clades that represent breeds that are related, genetically related, but also they have similarity in shape. And this work has also been possible from the availability of the Stanford Extra dataset. So it's a dataset of dog images with breed labels that has been recently annotated for silhouettes and 2D landmarks. So the idea of using the side information in the form of breed labels is that if we have that information, we can say that two pictures of, let's say, two husky, their shape it's more similar than the shape of an husky and a French bulldog. So Nadine designed this breed-aware reconstruction network that is composed by a stack hourglass and a shape branch and a pose branch. So there is an input image. The image is passed through this hourglass network to output a segmentation mask and key points. So then the segmentation mask and the image are processed with the ResNet to compute shape features, Z. And from these shape features, we predict breed labels and the betas for the small model, the model without the original small model. And the post branch takes the bone length and an encoding of the segmentation mask and the key points. And from this information predicts the 3D pose, translation, and camera. So at training time, we use a set of losses. So we have losses on the 2D annotations from the Stanford Extra dataset. We had some repriors, and then we have reprojection losses for silhouette and key points. But most importantly, we have this new breed losses, which are three. One we call breed 3D2G model loss. This is optional, and it means that in case you have a 3D shape, that 3D model that represents a specific breed, you can exploit this to recover fine details, right? Let's say fine face details. But the most important losses are this breed triplet loss and breed classification loss. And together we call them breed similarity loss, And the effect of using these losses is actually to add structure to this latent shape space. And this is demonstrated from this experiment. So we train a network without this breed similarity loss and with the similarity loss. And then at test time, we look at the Z for all the images, and we projected it into a 2D space. And then we visualize these 2D projections where we use colors to indicate breeds that belong to the clades on the right, that are the one corresponding to the initial cladogram. And different saturation for these points mean different breeds. And if you don't use similarity loss, these larger shapes, they indicate the average in the clade. So if we don't use the breed similarity loss, these average values, they all kind of merge in the middle, meaning there is no structure in the data. And if you use breed similarity loss, you see that there is a clear structure that emerges. So results are also like visually, they confirm the advantages of using this side information. We also look at reconstructing unseen breeds. So it works also for unseen breeds and for mixed dogs. And there is a project page where you can find the code, the paper, the project, so the poster, and the video. But Nadine has also done this great thing of putting a demo on Hugging Face. So you don't need to download the code if you want to try it with some images of your choice. And that's all. Thank you for your attention.
So Silvia, just to clarify, does that mean we can go on Hugging Face and upload an image of like our pet and get a 3D model?
Yeah. Yeah.
It's definitely happening.
That's awesome. Okay, well, thank you so much. So yeah, open for questions, please. Any questions from the audience? If not, I have a question. Yeah, I'll let you guys ask first. Go ahead.
When you were first building up your 3D models of taxidermied animals, how did you determine which taxidermied animals to use? Because there's so many in museums that were done so long ago and no longer, or they weren't accurately done, or they were stylized.
Yeah, so we didn't use taxidermy animals. So we scanned them. We scanned a few of them. And we realized that as soon as you remove the texture, they look completely unnatural. Because the way they are created, so they take the skin, they put some, I don't know, stuff in them. And the shape actually doesn't really look natural at all. So that's why we didn't use them. Also, we found some issues when you go to museums and ask if you can touch them, like a little bit to scan from this side. They're very delicate, and that's why we didn't use them.
Okay. So I think they used those tiny plastic figurines, that like little kid toys of all the different types of animals, which is cool.
Yeah, I have. We use guys. Some of them.
Yeah,
I guess my question, I'm not sure if you know, but how did they make the kids' toys if they don't know the 3D representations of the animals in the first place? And also, is your work used in like really cool movies, like animals and stuff?
So if I could understood the question, how did they make this? So these are actually made by artists, and And the company that makes this, actually, they say they have an agreement with the Berlin Zoo, where so the artists, they go there and they
Wow.
do the animals. So they're not very accurate in the sense that sometimes they have some to make them maybe look like aggressive. They have big mouths, and so I think that we need to improve the models using data from real animals. I think this direction is very useful. Using the small model because it provides an initialization when you have, like in the case of the smaller methods, you have an initialization and then you try to match data from real animals, like 2D data. But I think that maybe I cannot talk too much about future work that we are doing, but I think we are in the direction of learning from real animals.
Catherine?
Yeah, in the slide with all the zebras from the 2D images, the zebra 3D representations were all different sizes depending on how far away the zebra was from the camera. And I was curious, is there a way in your models to put all those zebras on the same scale so that you can then compare across sizes?
Yeah, so actually, we hope we could have zebras of different sizes. So the problem is that if you don't have a calibrated camera and you have a perspective camera, and so then there is ambiguity between the size of the animal and the distance from the camera. And so, and I think for having a metric reconstruction, that is accurate for the size, you need to have probably multiple animals together or some reference in the image. Essentially, if you look at the shape space, usually the first dimension really tells you about the size, and then the other dimensions, some like more details. And maybe for comparison, I think you can try to look at comparing directly the shape variables instead of comparing the models. I think that could be interesting. Yeah, I wish you could have big animals. We could have a easy way to have a metric, like for the birds paper from if you look at the 3D shape space that they recover for the birds, all the birds, they have the same size. That is because actually when you do these reconstructions, usually the method, the optimization of the network, they are kind of lazy, and they change instead of changing the model, if for them maybe it's easier to put the model closer to make it bigger and stuff like that, so you don't recover these relative size variations.
Hi Silvia, thanks so much for your talk. It's so interesting. I was wondering, obviously there's so many applications of the 3D models. I was wondering if there's any particular applications of this in ecology or zoology that you're most excited about, or that you can see coming this way.
Yeah. So so this moment, so C is this student that I'm co-advising with Hedvig Kestrom at ETH. And there they are looking at pain in horses. And this is a very important problem because how can you detect when an animal is in pain? It's really important for the well-being of the animals. And And so we are trying to look at this problem using 3D models to really be able to analyze the pattern of motion. So I like this direction of using these approaches to improve the quality of life for the animals. And I never really so the thing for the animal re-ID, this is what I thought I would have done immediately after we published the zebra paper. But in a way, in computer vision, you always try to run up and try to submit to the next computer vision conference, where sometimes the novelty in the application is not really appreciated. So maybe I should have done that a few years ago. Yeah, I think the identification, this animal behavior understanding are the two main applications that come to my mind.
Thank you.
Maybe one more question?
Yeah. In your work in dogs, when you recreate these models, can you distinguish between individuals from the 3D model? Can you distinguish between different individuals of the same breed, for example?
So if I have to, so I don't understand the question. So if I have two dogs of the same breed, if I get back two different dogs, or
yeah, from the models that you reconstruct, can you tell that they are different individuals?
Yeah, I think so, but we haven't tried. So we don't get always the same dog out independently of the image. That is the easy answer. So guess it depends how different the dogs are, and so it's hard to answer to this question. So I would like to actually, this makes me think about something that I think it needs to be done. Like we need to prove that these models, they have the sort of resolution that is necessary for the task that one has in mind. So this means you want to do gender, like as I said before, like pregnancy from pregnant zebra from a non-pregnant zebra. So then your model needs to be able to actually represent the pregnant zebra. So if you want to distinguish between, I don't know, an elephant with big ears from an elephant with small ears, your model needs to be able to represent the different. And so depending on what's your question or your biological or research question, you might need a model that has maybe even more body parts. Like if you look at just motion, maybe the 35 body parts of the small model are sufficient. If you want to look at face expressions in the animals, you need to have a different 3D model, but this is the same for humans, where you might have articulated hands or no hands, or you have face models that you combine with the body models.
Yeah, I imagine also, I think there's a lot of complexity using shape alone for individual re-identification, because body shapes change based on body condition. So if you're like, if you see an animal one season and it's starving, and then the next season there's been a lot of food, it's very difficult to say, yeah, this is the same individual in different body conditions, as opposed to this is a different individual. But I actually think that's very interesting. And particularly in cases where we have visual signals, like the texture or like things like these ear contours of the elephants, if we're better at re-identification, then maybe we can combine these approaches and get more nuanced and like very fine-grained body condition estimates.
One of the other things you can do, and it's also like it would be, yeah, in terms of the resolution, if you can ask, so if the body of one animal changes on like, I don't know, 10 kilograms, are you able to detect the change? Those kind of things.
Yeah. Awesome. Okay, thank you so much, Silvia. This was so interesting. Yeah, I think if it's okay with you, I'll send your email out so that if they're interested in following up, they can. Is that okay?
Yeah, sure.
Awesome. Okay, cool. Yeah, so thank you so much. We really appreciate you giving a talk, and yeah, let's just.
Have a nice rest of the summer school, everybody. Bye.
Thank you.
Okay.